Oh, here we go. Back recording. Get this going. Part two. First law of thermodynamics. Yeah, it's really just conservation of energy. You cannot create or destroy energy. You are allowed to transfer energy to different forms. We have a new form at this point, which is thermal energy. So yeah, have temperature changes. In this class, we mostly focus on the first two laws of thermo. There are a couple other ones too, but I remember the second law had something to do with entropy. Right, there's the time order processes. As time moves forward, statistically, energy loses quality. Right? That was the second law, but the first law was just straight conservation. You could use that to find like final temperature and like some equilibrium. Uh, what's the temperature increase due to a waterfall splashing? Right, you can do that. All right, we got some points on the board. Yeah. The greater the difference in temperature between input and output reservoir for a heat engine, well, a couple of you guys got that. Greater the efficiency. Right, so a few ways you can think about that. Oh, here's Carnot efficiency. So this is an ideal efficiency scenario, right? So you guys see temperature cold over temperature hot. So if you take that ratio, right? Now, if this ratio is really small, like closer to zero, so if you have very, very, very cold here and very, very hot here, right? 1 minus getting closer to zero is approaching 1 or 100%, right? So, okay, so that means you can increase your efficiency. That's what this Greek letter eta is by having a greater temperature difference, right? Another way to think of it, hey, do you guys remember the Stirling engine? Right? You guys remember I had a cup of hot water and I put this on a cup of hot water. Right. And then there was the hot sink was the hot water and the cold sink was, well, room temperature. Right. There was a temperature differential. And I got this to start spinning. Right. There was a whole process involved there. Yeah, what if there was no temperature differential? Like what if I just put regular room temperature water here? Would this spin it off? No, because there would be no temperature differential. Okay, so zero temperature difference corresponds to zero efficiency. I think that makes sense too, right? Right. And that's really more what I want you to get out of this class is how to think about things, right? How to think about things. And this is a classic example. Right, two identical blocks, one's at 10 degrees Celsius, the other's at 20 degrees Celsius, they're put in contact. Suppose you come back later and the cold one cools down even more to 5 degrees and the warm one warms up even more to 25 degrees. Ooh. Now that's never going to happen. Because why? Yeah, specifically the second law of thermo. Now, the first law it's actually safe according to the first law. Identical blocks being the same mass and the same materials and so on. So if one drops by 5 degrees, one picks up by 5 degrees, well, you say, well, the amount of energy transferred, right, that could actually check out. So it doesn't actually violate the first law. Right. But there's a time order of things, which is you would expect these two to want to reach an equilibrium. They want to reach the temperature in the middle, maybe 15 degrees, and these are doing the opposite. Yeah. So the second law of thermo is really a statistical law of the universe. For large systems, it always follows that. All right, you had some points. Running a refrigerator with its door open in a hot room makes that room. Oh. Yeah, it's gonna make that room warmer. Make that room warmer. Okay, I'm searching around my files. Do I not see this? I wonder if it's. Let me look up something real fast here. Okay. So, right. Here we go. Here we go. I was looking for this picture right here. Right here. Right. Guys, you ever walk through an old part of town or maybe a very old university sometimes and you see all these window units hanging out the windows? You guys see those? Right, these air conditioning units? Right? Well, why hanging out the window? Guys, could you plop a whole air conditioning system just in the middle of a room and it would actually make the room cooler? No, no, that'll never happen. Right? Because refrigeration which air conditioning and refrigeration are basically the same type technology. Okay? It's a process where you're starting with, say, lukewarm air, right? So room temperature air, right? And somehow you want to get something cold out of it, which is a really difficult type process to do. It took people thousands of years to figure that out, right? Heating something up is easy, right? You just light a fire, boom, done, right? People figured that out in like caveman days, right? But cooling something off, right? How do you like make ice out of room temperature? That's very, very difficult. It'll never happen spontaneously. You can never start with lukewarm air and it spontaneously gets cold and another mass spontaneously gets hot. Right? You can run that as an energy intensive process, but it is a whole process. So, guys, the fact that all these units are sitting in the windows, aren't they actually dumping the hot air out of the process out into the wider atmosphere? Yeah, and then the cold air gets dumped into the room and makes the room colder. Right? Same thing with your refrigerator, which I think actually was what the question was, is yeah, refrigerator. So refrigerator, all the cold air dumps out the front. But if you reach back behind the refrigerator, do you think there's a bunch of hot air dumping out the back? Yeah, because the laws of thermo, the first and second laws, right? Now, if you combine that hot air and the cold air, you might say, okay, well, at best, maybe it's a wash and the temperature stays the same. But that can't be the case because your refrigerator is, well, it's plugged into the grid. So it's importing energy from the grid, right? It's an energy intensive system. So in a way, the hot is always going to beat the cold. So if you mix the hot and the cold back together, yeah, overall, the room does heat up. Right? There's a cold part of this process, but the warm part is even warmer. Yeah, and so overall, the room's gonna heat up. Right? Yeah, that's definitely a good one to know. Ideal efficiency for a heat engine operating between those temperatures. Notice I gave you Kelvin temperatures, which is really nice. Guys, look at this ideal efficiency formula right here. 1 minus TC over T. So can you guys in your calculator do 1 minus and do 310 over 2050? Go ahead and do that. 1 minus, then 310 over 2050 should give you a decimal. All right, so you guys got that. Show you guys what I got. Okay. Right. I typed in that formula. Okay, this is Carnot ideal efficiency. Okay. If they gave you temperatures in Celsius, you would have to convert to Kelvin first. I gave you Kelvin already, so you just plug it in. I got 0.848 something something. Right. That rounds to 0.85. Oh, and as a percentage, that would represent 85%, wouldn't it? Yeah, yeah, yeah. Right. So if that was, for example, the case for the Stirling engine right here, right? What that would mean is there's a transfer of thermal energy from that cup of hot water that there used to be. You guys remember that cup of hot water right here? Right. Right. Going through this machine. Right? And it's causing like a whole process to go on here, gets things back. Turns this to mechanical energy. Hey, I bet I could calculate the mechanical energy of the spinning. And there's some thermal energy that's going through to initiate that process to begin with. If I had like 100 joules go through, and I got like 85 joules of mechanical energy spinning, that's what this would be right here. It would be 85% efficient. It would be taking 85% of that thermal energy and turning it to mechanical energy. Yeah. Right. So any machine you run, right? Put gasoline in your car, there's some percent efficiency, right? And then there's some energy that turns into like heat energy and waste forms that aren't helpful to like, making the car go. Okay. Oh, waves, standing waves. Yeah, all the above. Right. Now these are different categories of waves. So blowing across the top of a bottle, that sounds longitudinal, right? Because does it sound a pressure wave longitudinal? Right. But that could be a standing wave, could set up like a no. Guitar string. And then the guitar string itself, I think, would be more like a transverse type wave. That string actually flying around, going back and forth. Although that is compressing the air and creating air waves, which is what you hear as the musical note. That could be a standing wave. Organ pipes is probably very similar to blowing across the top of a bottle, right? Yeah. So right, standing wave where the nodes and the antinodes stay in place, the wavelength stays the same. All those things all come together. All different forms of standing waves. That bug is jiggling up and down and swimming towards you at the same time. Compared to the frequency the bug is emitting waves, the frequency of the waves reaching you. Oh, yeah. What would be a higher frequency? I'm looking for my Doppler. Ah, here's Doppler effect. Doppler effect. I got this. Isn't that this right here? There was a whole equation that went with it. Right, you could relate, right? But right here you are. Here comes the sound source. This car's beeping its horn. Boot boot. Right, and the waves are reaching you more frequently than they would be if both these objects had been at rest. Right, if the car had been parked. Right. Right. Now the car's moving towards you. These wave crests are reaching you more frequently. More frequently. Right. Right. As the car's horn passes and recedes away from you, the pitch of the horn seems to. Oh, okay. There's that picture. So what if you were standing on the red side over here? Yeah, the pitch, that's to say the frequency would decrease if the car's going away from you. Oh, I didn't ask about the speed though. Maybe I'll run back around to that. Right. Child swings back and forth on the playground swing. What if he stands rather than sits? Guys, if he stands, it's not like he's moving his center mass upward. Is that effectively shortening the pendulum? Shortening the pendulum? If you have a shorter pendulum, make this L really, really small, what happens to this T? Yeah, also gets smaller. Also gets smaller. All right, let's look at that formula again. Do you guys remember doing that experiment? You guys made different pendulums. You were testing different variables. What if I change like this mass? What if I change? You changed different things, but the variable that you changed that actually affected the time period was the length of the string. Okay. If you make the length of the string shorter, do you guys see that time period also has to be smaller? Right. That was the answer to that question. Right. And if this kid stands up, then he moves the center mass up, so it has that same effect. Right. Here, I do want to go back to the Doppler question just for a little bit because I thought I had thrown another question in here. But a good question that you could also ask is, guys, what happens to the speed of these waves when you put this car in motion? Does the speed of sound stay the same? Yeah, yeah. The speed of sound doesn't actually change, right? But the perceived frequency does, depending on which side of the car you're standing. All right, right. All right. Simple pendulum suspended in an elevator. Elevator is accelerating upward. Guys, if the elevator is accelerating upward, does it feel like somebody just turned up the gravity field? Turned up the gravity field? What if you pump up this G really, really, really big? Now what happens to the T? It gets really small. It gets really small. Let's look at that formula again. Okay. And so you run the formula. This pendulum swing back and forth. It takes some time to swing back and forth. Right. It takes some time. Right. Now you step in an elevator that's accelerating upward. Ooh, it feels like somebody just pumped up the gravity field. So now you're dividing by a huge number, which makes the overall fraction smaller. Now can you see that pendulum swinging back and forth, going back and forth really fast because it's like somebody just turned up the gravity. Could you guys go the other way? Right? What if you go to the moon? The moon has a really weak gravity field, doesn't it? Right. Now what does the pendulum motion look like? It's like whoosh, whoosh. Isn't it going back and forth really slow on the moon? Okay. It takes a long time on the moon. Right. Or if you were in a downward accelerating elevator, that would be the same effect, wouldn't it? So that's the opposite of that. Right. Right. Are you guys good with right? Changing the gravity field? How does that affect the pendulum? Sound wave has a higher frequency, has a wavelength that is this one right here. Yeah, a shorter wavelength. Okay. Here, I'll back this up with a little bit of math too. Okay. Because this is a important wave formula. You got speed equals wavelength times frequency. Okay. So wavelength. Okay. Frequency is like the musical pitch. If you say like I play an A note, that could correspond to like 220 hertz or something like that. Okay. And this is speed. Okay. And if we're talking about sound, well, the speed of sound is locked in place for given pressure and temperature in the room. Okay. So typically, like in this room, it's probably fairly close to. I'm just going to call it 340 meters per second. Okay. It's probably pretty close to that. Okay. Okay. So let's say as I'm talking, maybe I'm talking at 170 hertz. I'm just making something up. 170 hertz. Okay. Could you guys calculate what the wavelength would be? Here, I'll do it with you guys. So I'm looking at wavelength is equal to take 340 over 170. Okay. That'd be 2 meters. 2 meters. Okay. So you can see the compressions in the air molecules. There would be a 2 meter gap or something like that. Now, what if I double the frequency frequency. I'm talking really high pitch. Guys, does the speed of sound change? No, speed of sound's the same. Right. But let's get maybe I'll call it lambda 2. Ooh, okay. And now I'm talking in a high pitch. Maybe I just double the frequency. That's up a whole octave. Woo. Well, now the wavelength's only half as much. Okay. You guys see an inverse relationship between the wavelength and the frequency? Yeah, one of these gets bigger, the other has to get smaller, and vice versa. Right. But the speed will be the same as long as you're in the same room with the same air and all that. Leaf on a pond oscillates at 2 cycles per second. What's the frequency? Bleep, 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 bleep. 2 cycles per second. What's the frequency? It's 2 hertz. 2 hertz. That's all. Right. 2 cycles per second is 2 hertz. Right. Now, a little bit different question you could ask is, what's the time period between blips? In that case, you guys would have said what? 0.5 seconds. Right. Which is a different question and not on here at all. Right. Yeah. So 2 hertz does correspond to 0.5 seconds of time period. Right. Guys, isn't time period and frequency just reciprocals of each other? Right. Okay. So 2 cycles per second is 2 hertz frequency. And there would be a half a second between beats. All right. Radio waves travel at the speed of light. The wavelength of a radio wave received at 200 megahertz. Ooh, you have to do some conversions here. Wow. All right. Okay. Yeah. Maybe use some more time on that. Maybe. Right. Here. Show you this up. Right. So it said 300,000 kilometers per second, and we have oh, whoops. Sorry, this is backwards. Oops. Right. Sorry, we're solving for wavelength. Okay. And it gave you the frequency as 200 megahertz. 200 megahertz. Okay. Isn't that what it said? Something like that. Okay. Before I touch a calculator, I'm going to make some conversions to put these all in base SI units. Okay. 300,000 kilometers per second. I really want not kilometers per second, but what? Meters per second. So what do I have to do to this number? Yeah, add on 3 more zeros. Right. And now I have meters per second. There you go. Hey, that's 3 times 10 to the 8 meters per second. You guys see that number lots of times. Okay. And then how about mega? Guys, mega is what? Yeah, 6 zeros. It's a million. A million is 10 to the 6. Mega million. That's not too bad, right? Okay. All right, so if I take this and divide by this, now I do have to put some parentheses when I divide over. Let's do 3 times 10 to the 8 divided by, and then in parentheses, 200 times 10 to the 6. Right? I'm looking at lambda is 1.5, that's meters, 1.5 meters. All right, you guys good with 1.5 meters? Or how to calculate that? Okay. So we got speed is wavelength times frequency. The speed of all EM waves should be 3 times 10 to the 8 meters per second. Okay, and you can do a little division right there. You guys can get that? Sound waves cannot travel. In a vacuum. There you go. All right, so sound does require a medium. For example, these other two. Yeah, not through a vacuum. Although light can travel through a vacuum, but not sound. Noise canceling earphones. Ooh. Yeah, destructive interference. Okay. So suppose there's a wave of some crest here. Right? Hey, what if you had a machine, say noise canceling headphones that could respond to that and create sort of like the anti-wave, right? And then combine those two. Yeah, that would be destructive interference. Yeah, yeah, yeah. Right. Of course, sound's compression wave, longitudinal, so it doesn't exactly align with the picture, but it gives you the right idea. So high, low pressure points. Yeah, it could destructively interfere. How far away is a jet plane when you notice a 2 second delay between seeing the plane and hearing it? There's the speed of sound. 2 second delay. Can you guys go x equals vt? Distance equals speed times time? All right, there you go. All right. I wish I changed the story on this a little bit because a more relevant story could be: you guys ever seen a flash of lightning and then you wait a few seconds and you hear the thunder? Right. It's the exact same math because it's the same speed of sound, approximately 340 meters per second. Right. We're seeing a 2 second time delay. Let's say you see a flash of lightning, you count one, two, and then bam, you hear the thunder. Ah, that means 680 meters away is the lightning strike. 680 meters. Okay. Guys, good rule of thumb. If I put a 3 seconds right here, would this come out to very, very, very close to 1,000 meters? Not exactly, but very close. Okay, so every 3 seconds, here, I'll jot this down too. Okay. So approximately 3 seconds corresponds to 1 kilometer away is the lightning, between lightning and the thunder. Okay, let's go to American units. Every, maybe you guys know this, or maybe you've been told this. Every how many seconds corresponds to what, like American type distance? 5 seconds being 1 mile, right? Is that true? This ratio right here might look fairly familiar. The ratio of 1 mile to 1 kilometer is a 3 to 5 ratio also. Yeah. So if you count off 10 seconds, lightning must be 2 miles away. Okay. So which of the following fundamentally different from the others, like categorically different? Sound waves, light waves, radio waves, X-rays. One of those is categorically different. Yeah, sound waves, right? Because guys, all those other options, light, radio, X, are all examples of what? Yeah, electromagnetic. Yeah. This blue, this yellow, this green, they all travel at what we call the speed of light. It's really the speed of all electromagnetic waves, right? Right. But not sound, right? Sound travels about 1 million times slower. Sound requires a medium. Sound is a longitudinal wave instead of transverse. All these other three are transverse waves because they're all electromagnetic. Right? So categorically different. You guys get categorically different? Right? Just got that down in your notes. Main difference between a radio wave and a light wave is it's yeah, wavelength is a good answer. Uh, there also could have been another valid answer that I did not offer as a choice. Because what else could have also been a good answer? Frequency. Yeah, frequency. Yeah. Okay. So wavelength and frequency are both okay. Okay. But not speed, because these are all traveling at the same speed. They're all EM waves. Okay, so wavelength's a good answer in this case. Main difference between a radio wave and a sound wave. Yeah, basic nature. We're talking about apples and oranges now. Right? Radio wave is electromagnetic. Right? Sound waves, compression wave that you can hear in the air. Right? Those are two totally different things. Compared to speed in air, the speed of light in water. Yeah, yeah, is lower. There you go. There you go. Right. Right, so actually, when I've been saying all these waves travel at the speed of light and all the same, that's really only strictly true through a vacuum or through air. It's pretty close anyway. Right? But yeah, once you hit water, glass, right, plastic, right, yeah, there's this process where okay, the waves are going to slow down, and that sets off this whole refraction process, doesn't it? Right? Yes, how much the light slows down compared to the speed of light, say through a vacuum. Do you guys remember what that was called? That ratio of speeds? It was called the what of what?
Rate of inflection.
Yeah, yeah. Here's one of the words. Something of refraction.
Oh.
Started with an I. You guys remember index? Yeah. You guys remember index of refraction? Yeah. Yeah. Index of refraction. Okay. So, for example, if the index of refraction was 2, light would be going twice as fast through a vacuum compared to whatever material, like diamond or whatever it is. Right. Okay. Index of refraction of 2. It's going like twice as slow through the material. An electron vibrates up and down 1,000 times per second. It generates an electromagnetic wave with frequency of 1,000 hertz. Yep, yep. It's 1,000 times per second. Yeah, that's 1,000 hertz. Okay. Now the resulting speed you'd have to calculate from speed equals wavelength times frequency. Right. So now that you know the frequency, or wait, sorry, blah, blah, blah. What am I thinking? Scratch what I just said. Right, guys, you know what the speed's going to be. Guys, what should the speed be? Yeah, 3 times 10 to the 8 meters per second. All right, I'm being silly about that. Yeah, guys, 3 times 10 to the 8 meters per second, which is not that. Okay, wavelength is the one where you have to break out that formula and calculate. So, okay, so I know the speed is 3 times 10 to the 8 meters per second. I know the frequency is, say, 1,000 hertz. So the wavelength, I could do C equals lambda F, and then divide over the frequency, and then I could solve for the wavelength. So I could do that. Right? And how about time period? Guys, if this is bouncing up and down 1,000 times per second, what would the time period be? Is what?
1 second. 1,000 times a second. So
Yeah, one over 1,000 seconds. Yeah, it'd be 1,000th of a second, right? Because it takes 1,000th of a second to cycle once. Therefore, in a single second, it will have cycled 1,000 times, which is what the premise was, right? Right? You guys remember time period and frequency, or just reciprocals? Right? So frequency, 1,000 hertz. There you go. 2 polarizing filters held at right angles to each other. How much light is transmitted? Oh yeah, there's a good picture. We're holding those at right angles. Those polarizing filters. Zero light. Okay. So remember, polarizing filters only allow transverse waves to travel in one direction. Since light is a transverse wave, if you hold those polarizing filters perpendicular to each other, no light gets through. Okay. If you hold them parallel, then most light gets through. Okay. All right. Okay. That makes sense. Since polarizing filters. Right. Color seen on a TV. Yeah, color addition, color addition. Guys, that's this picture on the left. Okay. This might be one of the questions coming up anyway, but your phone screen, your laptop screen only has 3 colors. If you zoom down microscopic, if you're an ant crawling around, you really only see 3 colors, which are what, and what.
Red, green.
Yeah, red, green, and blue. That's all your phone screen has. Is just a red, a green, and a blue blip. That's all it has. Right. So how does your phone screen make white light?
It puts them all together.
Yeah, they're all lit up at the same time. That'll make white light. How does your phone screen make yellow?
It put red and green together.
Yeah, it lights up the red and the green, and to you that looks like yellow, from a distance. Our scale. Yeah, that's color addition. So anything related to a phone screen. Hey, what if you have flashlights and I have like a red bulb and a green bulb and a blue bulb, and I light those all at the same time? Does that create white light? Yeah, sure does. Sure does. Yeah. So anything to do with like light shining, screen shining, you have to use color addition. Right. But what about if you print a photograph? Now what? Yeah, that's color subtraction. Right. You guys have a color printer at home? Um, guys, what's the only three colors that are in your color printer?
Uh, yellow, cyan, magenta.
Yeah, these two right here. Yeah, yellow, magenta, cyan. Those are the three colors in your color printer. That's only the colors you get. No, you might have a separate cartridge that's just black, right? Right. But for the colors, right? And out of these, you can create any color that you can see on a printed page, right? Um, yeah. So how do you make a nice deep red on your picture?
Magenta, yellow.
Yeah, it's magenta and yellow at the same time. Right, so to our eyes that look right? Because now the more colors you add, it subtracts out the wavelengths until if it runs all three at the same time, you could get blacking that way. Yeah.
Just
Colored dots that make up the color on the TV screen.
red.
There you go. All right, red, green, and blue. RGB standard, red, green, blue. That's all you need. Law of reflection. Uh, it says the angle of reflection from mirror equals the angle of incidence of reflection. Right. Okay. Guys, that's here's a picture right here. So if you were to follow a single beam of light from say that candle bouncing off that mirror, it's gonna notice I'm measuring with respect to this dashed off normal line. There's the angle of incidence in blue. There's the angle of reflection in green, right? And it always matches. Right. Now that's a flat plane mirror, but even if you have a curvy mirror at every single incident point on the mirror, right? And also you can have lots of beams of light. Here I'm just following one ray of light, but you could have like a million rays of light in all different directions. They all follow this law for a mirror. Yeah, angle of reflection matches the angle of incidence. Okay. You guys see there? Okay. And you know what? I was trying to dig around my files and find these lamps lighting. So I found this picture too for you guys. Right. Hey, look, I got three colored lamps. I have a green lamp here, blue lamp here, red lamp here, and oh, look at that. They mix to make white light. Okay, so that goes back a couple of questions ago. Do you guys remember that too? All right. A little color theory there. All right, got these.
Too late.
All right.
All right.
Yeah. All right, so you guys go with law of reflection. Law of reflection. Person standing waist deep in a swimming pool appears to have short legs because why?
Rabbits.
Yeah, refraction. Refraction. Yeah. So that could be that right there, right? You stick a pencil in water. Right? The pencil, of course, is actually straight, right? But the light bends, and then look at this angle of this light entering your eye. Your brain thinks it came from this direction. So now the pencil looks a lot shorter than it actually is. That's refraction. 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 Shortest plane mirror, you can see your entire image.
Never saw it.
Ooh, well, you kind of see it right here. Guys, here's the object. Here's his reflection, the image. Here's a plane mirror. Right. You guys see how much mirror you need compared to his actual height? Just have since made a whole poster for just for that question, but I had time. Yeah, it turns out they have to height. So if you are 6 feet tall, you can see your entire reflection with just 3 feet of flat mirror. Right. Now the catch is you have to have just the correct height level for that to happen. Okay, here, let's look at this picture again. Okay. Because guys, if I measured this guy's height, it was like 3 centimeters tall, or scratch that. Sorry, if this guy was 6 centimeters tall, 6 centimeters tall. You only need 3 centimeters of mirror right here. It's just here's the top of his head, here's the bottom of his feet for to see his entire reflection. Okay. Guys, next time you're in front of a mirrored surface, try this out. Look at where the top of your head is in the mirror. Look at where the bottom of your feet, like where your shoes are in the mirror, if you can see your entire reflection. Okay. And make either a mental note of where that is on the actual mirrored surface, or you could go up to the mirrored surface and like, put a little smudge with your thumb, right? Put a little smudge on the mirror, and then start backing away. And I guarantee you that where the top of your head is, where your shoes are in your reflection, are showing up in the exact same locations on the mirror. It doesn't actually matter how close or far away you are from the mirror either. Right? If you're 6 feet tall, you really only need 3 feet of mirror to see your entire self. A rainbow. Oh, okay. There's some refraction going on. There's also some internal reflection going on. There's both of the above. Let's look back at the diagram. Right, here we go. Right. So, here comes sunlight, white light, which is really all the colors. Right. Now, here's a couple of raindrops. To see this full rainbow, you probably need like millions and millions of raindrops. Right. Right. But let's follow a couple light beams here. So here's a light beam. Do you guys see some refraction right here? Refraction. Right. But then the light might bounce off the back of the raindrop. That's internal reflection. You guys remember total internal reflection? Oh, yeah, go. Yeah, go. Okay. And then it could refract again. Okay. And then if you follow the red light, it's coming in at this angle at 42 degrees. And if you follow a violet light, it's coming at this angle at 40 degrees. Right, here's the observer. Okay. Guys, next time you see a rainbow, where will the sun always be relative to you and the rainbow? Yeah, behind you. Yeah, guys, the sun is always behind you. If you notice that, right? And the rainbows, okay, in front, we're looking. Right. Yeah, so you have both processes going on. Okay. Actually, there's a little bit more to this too. If you get a really good effect, you can get a double rainbow. So there's a little bit different process going on here. Maybe show. Okay. That's the main rainbow right there. Okay. Reflection, internal reflection, or refraction, internal reflection. It's all going on. All going on. Chromatic aberration. Okay. Right. I don't really like my picture for that. I've definitely updated that in the meantime. Right. Yeah, so this Kahoot review is about a year old. Right, but right. Here's some classic refracting telescopes. Here's one Galileo used. Here's one that Kepler used. Right. They have different type lenses, right? Both they have a converging lens here, but they went with a different eyepiece lens. So here's a diverging lens, and here's another converging lens, right? And you get different type images. Right? So you could definitely magnify something like this. A galaxy might be way off in space, really hard to see, right? But of course it magnifies and it blows it up. You can see it easier. That's what telescope is for. Okay? But the disadvantage of this model telescope, well, either one of these, is well, it goes back kind of to that rainbow that you're looking at, or I think I can pull that out. It's kind of right here. It goes back to this, okay? Which is that if you got some regular white light coming in, every time it refracts, it's going to spread out a little bit. Every wavelength of the light refracts a little bit differently. Okay? So the colors spread out. That's what chromatic aberration is. The colors spread out. So you can't get exactly a nice crystal clear image of what you're trying to see. Okay? But there's a solution to this, which is to replace one of these lenses with a mirror. Actually, Isaac Newton figured this out. Isaac Newton said, hey, I'm just going to put a converging mirror right here. And then this light from the distant universe comes in, parallel line, pretty much. Right, it's going to bounce off this mirror, bounce. Right, maybe there's a lens here. Right, but he got rid of all of this chromatic aberration, so now he gets much crisper image. Right, all modern day telescopes are Isaac Newton's design. Right, so like the Hubble telescope, the James Webb telescope, they all merge from that. A magnifying glass will magnify how underwater compared to used in air. Yeah, not as well. Not as well. Okay. And it has to do with comparative indices of refraction. Wait, what did I show up here? Wow. Okay. Okay. Here, guys. Glass might have an index of refraction of let's call it 1.5 ish. Right. Water is about 1.33, and air itself is very close to 1.0. Right. So if you're going from air to glass to air, like a regular magnifying glass, that's like index refraction of 1 to 1.5 to 1. And you can run Snell's law, and right, it'll have a huge refraction. Okay? But if you're going from 1.33 to 1.5 to 1.33, that's not as much. You can run Snell's law over it, and it's not going to be as much refraction. Hence, you're not going to get as much magnification, which you guys correctly said. Oh, that's it. All right. On the podium, we got with the bronze, Gian, with the silver, Talia, and the gold, Oide.